Chapter 1.4, Limits and Derivatives. Alright, so in section 1.3, we first discussed limits in defining the slope of the tangent line. The tangent line was the limit of the slope of the secant line as h went to 0. Now we're going to discuss this concept in a more general way. So here's the definition of a limit. Let g of x be a function, a number. We say that the number L is the limit of g of x as x approaches that number a, provided that g of x can be made arbitrarily close to L, kind of like how the tangent and secant lines got close, by taking x as close as we can but not equal to that number a. If that's a situation where we're talking about numbers now and h is not going to 0 like we're used to, we write this as you see it below down here. Here's the notation. Okay, so the function to the right is f of x equals 2x minus 1. It's a linear function. So if we said let x approach 4, that is the limit as x approaches 4 of g of x. And then L is what we are saying is our limit. That's what it's going to equal. So when we do this, when we approach a number, we approach from two sides. We have the left side, and when we say that we're going to approach it from the left side, this means we're going to approach 4 from the negative side, which is the left side. You think left on the x-axis, you think negative numbers. And then we have the right side, and you say 4 positive. Okay? Notice how the minus and plus sign are on the right side. If they were in front, that would look like negative 4 and positive 4. So being on the right side of the 4, they are represented that they're approaching 4, but from which direction. So let's take a look at this in an algebraic way. So given the function that we just dealt with, 2x minus 1, determine the limit as x approaches 4. So remember, x can be close to 4 but not equal to 4 like we began. So we're going to use the numbers on the left side and the right side. Notice how both sets of numbers are close to 4 and then get even closer. So if we have 3.9, we are going to write this as 2 times 3.9 minus 1. And when you solve that, you get 6.8. So you're going to do that for every single value that's getting you closer and closer to 4 on the left side. And if I continue down my chart, I would get 6.98, 6.998, and then that last one is 6.9998. Okay, can you see what number it's approaching? Alright, so now we're going to go on the right side. And on the right side, it's the same concept, and I'm going to start with 4.1. So 2 times 4.1 minus 1 gives me 7.2. And then if I did 4.01, then I would get 7.02, followed by 7.002, and then 7.0002. All right, now, what value is the function approaching as x approaches 4 from the right side and the left side? 7. All right, so what do you think's going to happen if you investigate f of x as it approaches 3. Alright, so take a moment, pause this video, and try to fill out this chart and see what it approaches. Okay, so you should get 5.2. 5.02, 5.002, and 5.0002. Okay, so I caught my mistake. So I'm sorry that I would love to fix it, but I already made copies for you guys, so I apologize from this. So the right side should have these values, and the left side should have these values. So my 5.2s that I just wrote down should be from the right side. So why don't you make it simple and change this to right and this to left? And I'm so sorry because that does not even follow what we did up here, and I so wanted it to. So you can do that. You can switch just the words left and right, or you can switch your values, 3.1 and the 2.9. I'm so sorry, guys. You know that that's going to bug me so much. All right, so from the left side, we are dealing with the 2.9. So what you're going to get when you plug that in is 4.8, 4.98, 4.998, and 4.9998. So again, what number are we approaching? We are approaching 5 from both sides, the left and the right side. Okay, so we just finished talking about approaching at a value now, and now we're going to talk about some graphical things. So there's 3 things that we need to know about some of the graphs that we're going to see. There's something that is called removable discontinuity. This is where a point at which the graph is not connected but can be made connected by filling a single point. So that hole right there, if you fill that one hole at 2, 4, then it will be connected. And if I filled that in, the limit as x approaches 2 is going to be 4. All right, so jump discontinuity is a point where the function has finite but unequal limits as x approaches the point from the right and the left side. So if we looked at the limit as x approaches 3 down here, then if we approach from the left side, we'd be coming from this way, and we would get 3, and if we approach from the right side, we would be at 4. So they are unequal, okay? And then when you have non-removable discontinuity, this is where the x value of the function makes that denominator 0, which creates an asymptote. So think of like your rational function. So you know what an asymptote is. So as the limit approaches 3 here, then again, from both sides, we are approaching a, we're not approaching a number. We're going towards an asymptote, so that's not going to work. So at the bottom, we just summarize that. So things to consider when looking at a graph to determine the limit of the function. Check limits from right and from the left. We did that just a second ago, and we can do that on the one that has a hole above. So if we went from the left, our line is approaching, so at 2, our line is approaching 4, and it is from the right side as well. Okay, so check it from the left and the right, and we're getting the same value. So that's my limit. Number 2 says if the limits don't approach the same number, like in this scenario, When approaching from the left and the right, then the limit does not exist. And then that third is if the limit does not approach a fixed number. So it's approaching the asymptote, but the asymptote means it gets really close but never touches, so it's never going to hit that number. And we know that infinity is not a fixed number, neither negative infinity. So therefore, once again, the limit does not exist. And when I ask you like a limit question, you can easily write like equals dne does not exist. Okay, so I'm just going to sketch a graph and show you kind of how we kind of analyze these limits. Okay, so here's a sketch of a quadratic that is upside down, opening down. So as the limit approaches 1, so at this point 1, we have a point that approaches this number right here. And for this scenario, that limit is going to be 3. So graphically speaking, as I come from the left and the right, actually I should write it like this. I should write it horizontally. As I come from the left and from the right towards 1 on the x-axis, I approach the value 3. All right, we have a sketch of that cubic above. So at -1, which would be right here, then we have this point where this is going to equal 2. So once again, as I come from the left, the green function, and as I come from the right, the green function approaches -1 and gives us a value of +2. Okay, and our last example is a rational function, and that asymptote is actually going through -2 right here. Okay, so if I come from the left side on my rational function here towards -2, because that's what I want, then my function is approaching positive infinity. That's the first indicator right there, but then just to make sure we're sure, as we approach from the right side, we're approaching negative infinity. And remember, negative infinity or positive infinity, either one, it doesn't matter which one you have, means that the limit does not exist because that is not a fixed number. Okay, so on page 94 of your textbook, there are 6 limit theorems that are listed. These are them. We're going to work with them a little bit on this case and for some of the homework, but you will actually see these a little bit later, and definitely if you are moving on to AP Calculus. So they're good to know. It's a notation thing, so just please make sure that you tune into that notation. Okay, so according to the table that you have above, if I have the limit of x cubed as x approaches 3, then what I can do with the that power is apply it to the whole limit now and not just the x to the third. So I can write the limit as x approaches 3 of x as a quantity to the third. So what this lets us do is evaluate that inside now, and I take 3 and it becomes x. So as x approaches 3, the limit of x is going to become 3, and now I have 3 cubed, which is 27. All right, so in number 2, there's a couple things going on. So I'm going to first do the same thing I just did with what's being squared, but that coefficient also comes out in front, like that second example down on your chart. So 5 is going to come out in front, and then I have the limit as x approaches 2. And then I have of x squared, but now I can say of x and then the whole quantity squared. And then when I have a sum, I can separate them as well. So I'm going to have another part plus the limit of x approaching 2 of 7. So if we evaluate the first one, then we have the limit of x approaching 2 of x, which it's going to approach 2. So I have 5 of 2 squared, and then the limit of 7 as x is approaching 2 is a constant, so it's 7. So this gives me 27 as my final answer. And then in number 3, when you have a radical, the same thing is going to happen. So we have the limit as x approaches 1, x squared plus 8 can all now be raised to the 1/2 power. And then we can simplify inside as well and say the limit as x approaches 1 of x, this whole quantity squared, plus the limit as x approaches 1 of our constant 8, and then this whole thing to the 1/2 power. All right, so that is going to give us 1 squared, which is 1, plus our constant 8. And then that whole thing is going to be rooted, or take it to the 1/2 power. So I'm going to get 9, and the square root of 9 is 3. And then this last one, we are going to take that 4 and bring it out in front and just say the limit as x approaches 5 of x all squared. So we have 5 squared, which is 25. So this is going to give me 100. Okay, so we're going to stop here for the notes. I hope that you are kind of following along with me in my general ideas. I'm so sorry about the mistake on page 1. Make sure you fix that in some way. Knowing me, I'll probably recopy you a front page. So just make a note now of how algebraically we can prove that what the limit is of a number. And now we have the idea that if we're approaching a number, we are approaching it from the left side and the right side. Please also know the notation of that. If we're approaching 4, it's 4 with a minus sign from the left, and it's 4 with the plus sign also on the right side coming from the right. All right, so with that being said, we also have to know how to visibly take the limits when we're talking about graphs. So we have removable discontinuity, jump discontinuity, and non-removable discontinuity. So removable discontinuity is when it exists, but yet if we can just replace it just with 1 point, we can still find the limit. A side note, if there is no discontinuity, we can obviously just find the limit, like that linear function that we had at the beginning. So maybe flip back to that page and take a look. If it's a line or a continuous graph, then you just approach from both sides. So if there is a hole, that's okay. We can fix that continuity with just 1 point, still being able to find my limit. However, if we have a break in the graph that allows me or causes me to approach an x value from both sides getting 2 different y values, then that is not okay. The limit does not exist. And then if we are approaching an asymptote, or if we have an asymptote and then we're approaching not a finite fixed number, so infinity or negative infinity, the limit also does not exist. And then the third core concept were these 6 limit theorems. I understand you might feel like you're just substituting, and you can definitely go ahead and start there to check to make sure that your notation is telling you the same thing. So just kind of like what we worked on last class where you felt like you wanted to skip a couple steps. I get it, but it is so important that you understand all of these theorems and all of the steps that you can do to simplify and find the limit algebraically again. I hope you guys have a great weekend. Start your, I think Yeah, you already did that. So start your homework and work together if you have some time, and get your questions answered if you can. If not, see me when we come back on Tuesday. We don't have class, but you can still ask me questions and come see me. I hope you guys have a great long weekend.